Here is today's problem. We have an equation with two variables, x and y. The equation is written as x divided by y plus y divided by x is equal to 2. We want to find the mathematical relationship between the variables x and y that makes this statement completely true. We are adding two fractions together. The first fraction has x in the numerator and y in the denominator. The second fraction has y in the numerator and x in the denominator. These two fractions are reciprocals of each other. Two expressions are reciprocals if their mathematical product is equal to exactly 1. We can readily verify this by multiplying x divided by y divided by x. We multiply the numerators together to get x times y. We multiply the denominators together to get y times x. Because the mathematical property of multiplication is commutative, y times x is exactly the same as x times y. We now have the quantity x times y divided by the quantity x times y. Any non-zero quantity divided by itself is perfectly equal to 1. The product is 1, which confirms they are indeed reciprocals. We introduce a new algebraic variable called u. We define u to be exactly equal to the very first fraction. Let u equal x divided by y. If u is explicitly equal to x divided by y, the reciprocal of u represents the exact value of the second fraction, y divided by x. The reciprocal of u is simply written as 1 divided by u. We replace the fraction y divided by x with the new algebraic expression 1 divided by u. We rewrite our entire original equation using the single variable u. We replace x over y with u. We replace y over x with 1 over u. The right side of the equation remains 2. Our fully substituted equation is now u plus 1 divided by u is equal to 2. This equation contains a variable located in the denominator. To clear the denominator completely from our workspace, we multiply every individual term on both sides of the equation by u. We multiply the entire left side by u, giving us u times the grouped quantity u plus 1 divided by u. We multiply the right side by u, giving us 2 times u. We distribute the variable u across the terms on the left side. We multiply u by the first term, u, which produces u squared. We multiply u by the second term, 1 divided by u. When we mathematically multiply u by 1 divided by u, we get u divided by u. This evaluates and simplifies to exactly 1. The left side simplifies beautifully to u squared plus 1. The right side remains to u. The updated equation is u squared plus 1 is equal to u. This is fundamentally a quadratic equation because the highest mathematical power of the variable u is 2. We put the quadratic equation into standard form by systematically moving all terms to one side of the equals sign so the other side equals 0. The standard form of a quadratic equation is mathematically defined as a times u squared plus b times u plus c equals 0. We subtract the term to u from both sides. We insert the negative to u between the u squared and the positive 1 to arrange the terms in strictly descending order of their algebraic exponents. This rearrangement gives u squared minus 2u plus 1. The right side is 2u minus 2u, which evaluates to exactly 0. The final quadratic equation resting in standard form is u squared minus 2u plus 1 equals 0. We use the quadratic formula to thoroughly find the valid values for u. The quadratic formula states that for an equation in the exact form au squared plus bu plus c equals 0, the mathematical solutions are u equals negative b plus or minus the square root of the grouped quantity b squared minus 4ac, all entirely divided by 2a. From reading our standard form equation, the leading numerical coefficient a is equal to 1. The middle numerical coefficient b is equal to negative 2. The final constant term c is equal to positive 1. We substitute these three numerical values directly into the quadratic formula framework. We begin with u equals the negative of b. Since b is the number negative 2, the negative of negative 2 becomes a positive 2. We write a positive 2. We write the plus or minus mathematical symbol. We calculate the discriminant, which is the specific expression b squared minus 4ac located inside the square root boundary. We have the value negative 2 mathematically squared. Negative 2 multiplied by negative 2 is positive 4. We have the subtraction of 4 times a times c, which is minus 4 times 1 times 1. 4 times 1 times 1 evaluates to 4. Inside the square root boundary, we are evaluating the expression for minus 4. For minus 4 is exactly 0. The mathematical discriminant is exactly 0. We take the square root of 0, which is just 0. When the calculated discriminant is exactly 0, there is exactly one distinct real solution for the targeted variable. We plug this evaluated 0 back into the full formula. We have u equals 2 plus or minus 0, all entirely divided by 2 times a. Since a is equal to 1, the denominator evaluates to 2 times 1, which is 2. The total expression neatly simplifies to u equals the quantity 2 plus or minus 0, divided by 2. 2 plus 0 evaluates to 2, and 2 minus 0 also evaluates to 2. The numerator is securely established as 2. We have u equals 2 divided by 2. 2 divided by 2 evaluates to exactly 1. We have successfully solved the quadratic equation. The variable u is exactly equal to 1. We recall the original definition of our substitution variable. We intentionally defined u to mathematically equal x divided by y. We actively substitute the numerical value of 1 back into this definition. We replace u with 1, resulting in the algebraic equation. 1 is equal to x divided by y. We can read this mathematically as x divided by y is equal to 1. To successfully isolate x, we multiply both sides of this equation by the variable y. On the left side, x divided by y mathematically multiplied by y structurally cancels the y terms, leaving just the isolated variable x. On the right side, the number 1 mathematically multiplied by the variable y is simply y. We arrive at the exact mathematical result. X is equal to y. We discard the case where they are equal to 0 due to the original fractions, so the valid solution is any other completely identical pair. This definitive statement establishes that for the original mathematical equation to be fundamentally true, the exact numerical value of x must perfectly match the exact numerical value of y. We formally verify our mathematical result to guarantee correctness. We take our proposed identical solution and substitute it directly back into the original starting equation to definitively ensure it produces a completely true mathematical statement. The original starting equation is x divided by y plus y divided by x equals 2. We substitute the variable x with the variable y everywhere it structurally appears in the written expression. The first mathematical term is x divided by y. Replacing x with y makes it physically y divided by y. Any defined non-zero number mathematically divided by itself perfectly equals 1. The first term fully simplifies to 1. The second mathematical term is y divided by x. Replacing x with y makes it physically y divided by y, which also perfectly simplifies to 1. We fully reconstruct the left side of our testing workspace. The simplified first term is 1, and the simplified second term is 1. The arithmetic sum of 1 plus 1 evaluates to 2. The right side is precisely established as 2. The equation to equals 2 is a flawlessly true mathematical statement. Both sides exactly hit the perfectly matched target value. We perform a rigorous numerical verification. We pick an actual real number to independently test, following our derived solution rule that x must be numerically equal to y. We set the variable y equal to the integer number 7. According to our derived solution rule, the variable x must also evaluate to the integer 7. We mathematically plug the integer 7 into the original equation for both structural variables. We logically get 7 divided by 7, algebraically plus 7 divided by 7. The physical operation of 7 divided by 7 equals the integer 1. We have the foundational arithmetic addition problem of 1 plus 1. 1 plus 1 exactly equals 2. The original starting equation holds completely and utterly true under this strict numerical test. We additionally test a negative integer. We explicitly set the variable y equal to the value -4. This mathematically dictates that the variable x must also evaluate to exactly -4. We rigorously substitute these precise negative values into the original starting equation. We mathematically get -4 divided by -4, algebraically plus -4 divided by -4. A negative real number mathematically divided by a matching negative real number fundamentally results in a precisely positive real number. -4 numerically divided by -4 is exactly +1. The structural second fraction is identically -4 numerically divided by -4, which additionally evaluates to +1. We have the arithmetic expression 1 plus 1, which securely equals 2. The underlying mathematical structure remains perfectly consistent. We perform one absolute final numerical verification strictly using pure fractional values. We let the variable y exactly equal the fraction 1/3. Consequently, the variable x must also exactly equal the precise fraction 1/3. We securely substitute these independent fractions into the testing equation. the initial mathematical term explicitly becomes the fraction 1/3 divided by the fraction 1/3. To perfectly perform this division, we take the given fraction located in the numerator, which is 1/3, and we mathematically multiply it by the precise reciprocal of the fraction located in the denominator. The mathematical reciprocal of 1/3 is explicitly found by algebraically flipping the numerator value and the denominator value, giving us the new fraction 3/1. We multiply the original fraction 1/3 by the reciprocal fraction 3/1. We mathematically multiply the top numerators. 1 algebraically multiplied by 3 precisely equals 3. We mathematically multiply the bottom denominators. 3 algebraically multiplied by 1 precisely equals 3. We visually arrive at the combined fraction 3/3, which perfectly simplifies to exactly the integer 1. The second mathematical term is visually identical in every way, the fraction 1/3 structurally divided by the fraction 1/3, which completely evaluates to the integer 1. We systematically add the two successfully evaluated terms together. The arithmetic sum of 1 plus 1 exactly equals the target integer 2. Every single independent mathematical test perfectly confirms our rigorous algebraic result. The complete established solution to our starting rational equation is simply x equals y. Thank you for thoroughly watching. Please strictly like and subscribe.